In this chapter, we will discuss the rates of chemical reactions. In previous chapters, we have discussed the thermodynamics of chemical reactions. Thermodynamics is very important because it determines the equilibrium of a system. That is, what products and with what amounts can we get from a reaction. For example, the production of ammonia from nitrogen and hydrogen is spontaneous at room temperature. The huge equilibrium constant leads to almost complete conversion. On the other hand, the kinetics of a chemical reaction is also very important, because it determines how long it takes us to get that much product. For example, the reaction between hydrogen and nitrogen in gas phase is extremely slow. In industry, Haber process with iron bases catalysts is used to greatly accelerate the reaction. Usually, a larger motivation, that is, a more negative reaction gives free energy, leads to a faster rate. Unfortunately, it is not always the case. For example, the oxidation of iron and aluminium have similar chemical reaction equations. Both reactions are spontaneous. The Gibbs free energy of the reaction of the oxidation of aluminium is more than twice of that of iron, but the oxidation of iron is obviously much faster than that of aluminium. Such difference in chemical kinetics cannot be explained by thermodynamics. For simplicity, in this chapter, we will only discuss the chemical reactions in dispersions, that is, gases and the solutions. In a dispersion, the rate of a chemical reaction is measured by the change of the concentration of a reactant or product. For example, the reaction of hydrogen and iodine to form hydrogen iodide in gas phase. The rate of this reaction can be measured in terms of the rate of the change of the concentration of any species. Pay attention, the value of the rate depends on the species selected. The rate of change of hydrogen is the same of that of iodine. But the rate of the change of hydrogen iodide is twice the opposite of that of hydrogen and iodine. So, it is necessary to specify the species when the rate is mentioned. It is inconvenient, and may even introduce confusion. It is a good idea to use the rate of reaction instead of the rate of a particular species. The rate of reaction is the rate of the change of the concentration of any product, divided by its stoichiometric number. The rate of reaction can also be defined using the concentrations of the reactants. However, pay attention, the stoichiometric numbers of the reactants are the opposite of the numbers appearing in the equation. As a result, the rate of reaction is independent of the species selected. For example, the rate of reaction of the previous reaction is half of the rate of the change of the concentration of hydrogen iodide. It is also the opposite of the rate of the change of the concentration of hydrogen or iodine. According to the results of a lot of experiments, scientists found that the rates of chemical reactions depend on the concentrations of the chemical species. A rate law is an expression for the rate of a particular reaction in terms of the concentrations of chemical species and some constant parameters. In most cases, the rate is independent of the concentrations of products. The law of mass action is the proposition that the rate of a chemical reaction is directly proportional to the product of the concentrations of the reactants to the power of their partial orders. The proportionality coefficient in the law of mass action is called the rate constant. It is independent of the concentrations, but dependent on other conditions such as temperature. The sum of all the partial orders is the order of the reaction. Pay attention, though the law of mass action looks like the denominator of an equilibrium constant, the partial orders are not necessarily the stoichiometric numbers. When the reaction is elementary, that is, without any intermediate, the partial orders are equal to the numbers of molecular entities that are involved in the microscopic chemical event. For example, the oxidation of thallium-1 cation by cerium-4 cation without catalyst is an elementary reaction because one thallium-1 cation and two cerium-4 cations collide and react directly without any intermediate. The partial order of thallium-1 is 1. The partial order of cerium-4 is 2. The order of reaction is 3. Here, I also show you some stepwise reactions, which involves intermediates. The reaction between hydrogen and iodine to hydrogen iodide is a stepwise reaction, even though it has a rate law which is identical to an elementary reaction. In other examples, the rate laws are different from elementary reactions. Thus, it is impossible to distinguish a stepwise reaction from an elementary reaction just by its rate law. Chemical equilibrium and chemical kinetics are closely related to each other. Consider a reversible reaction. Both the forward and backward reactions are elementary first-order reactions. The rate of the change of the concentration of the reactant is equal to the rate of the appearance of the reactant due to backward reaction, minus the rate of the disappearance of the reactant due to forward reaction. When the system is in equilibrium, the concentration of the reactant does not change. That is, the rate of the disappearance is equal to the rate of the appearance. Thus, the ratio of the concentration of the product to that of the reactant is the ratio of the forward rate constant to the backward rate constant. On the other hand, the ratio of concentrations is close to the ratio of activities. The ratio of the activity of the product to that of the reactant is the equilibrium constant. Thus, the equilibrium constant is directly related to the rate constants. Chemical reactions can be categorized into different groups by their reaction orders. A zeroth order reaction is a reaction whose rate is independent of the concentration of any reactant. As a result, the concentrations of the reactants decrease linearly with time. Meanwhile, the concentrations of the products increase linearly with time. For example, the decomposition of ammonia on tungsten surface is a typical zeroth order reaction. The concentrations of both nitrogen and ammonia change linearly with time. A reaction is a zeroth order reaction when the material that is required for the reaction to proceed, such as the surface of a catalyst, is saturated by some molecules. Such phenomenon is called poisoning. In the previous example, the decomposition of ammonia takes place on the surface of tungsten. There is an equilibrium between ammonia in the gas phase and ammonia adsorbed on the tungsten surface. Only a small fraction of ammonia on the tungsten surface undergoes reaction per unit time. The adsorption of ammonia on tungsten is energetically favorable. So, the tungsten surface is usually fully covered by ammonia. The number of adsorbed ammonia molecules does not increase with the increase of concentration of ammonia in the gas phase. Therefore, the rate of the reaction does not change, and the reaction is a zeroth order reaction. A first-order reaction is a reaction whose rate is proportional to the concentration of one of the reactants. The simplest first-order reaction is a reaction from one reactant to one product. The rate is proportional to the concentration of the reactant. The time evolution of the concentration of the reactant is an exponential decay. The time evolution of the concentration of the product can be calculated from that of the reactant. The concentrations of the reactant and product with given initial concentrations are shown in the figure. The most important feature of a first-order reaction is its half-life. Half-life is the time required for a quantity to reduce to half of its initial value. Using the time evolution of the concentration, we can find the formula of the half-life. Note that the half-life of a first-order reaction is independent of the initial concentration, vice versa. If a reaction's half-life is independent of the initial concentration, the reaction is a first-order reaction. The rate constant can be replaced by the half-life. The time lapse can be calculated from the ratio between the initial and final concentrations. For example, beta decay is a first-order reaction, despite of that it is not a chemical reaction but a nuclear reaction. The beta decay of carbon-14 has a half-life of 5,730 years. The technology using the concentration of carbon-14 to determine the ages of fossils is called radiocarbon dating. It is widely used in paleontology and archaeology. Carbon-14 is produced by thermal neutrons absorbed by nitrogen atoms. When cosmic rays enter the atmosphere, they can produce neutrons. The resulting neutrons participate in the so-called NP reaction. Plants fix atmospheric carbon during photosynthesis, so the level of carbon-14 in plants and animals when they die approximately equals the level of carbon-14 in the atmosphere at that time. However, it decreases thereafter from radioactive decay, allowing the date of death to be estimated. For example, a fossil has 1% carbon-14 to carbon-12 ratio compared to the initial value. What is the age of it? The answer is about 38,000 years. A first-order elementary reaction is called a unimolecular reaction, in which a molecular entity reacts by itself. For example, the decomposition of dinitrogen pentoxide is unimolecular. Experimental results show that its half-life is a constant. The plot of logarithm of concentration versus time is linear. There are two types of second-order reactions. In type 1, the reaction is second-order with respect to one reactant. The simplest reaction of this type has only one reactant. The rate is proportional to the square of the concentration of the reactant. The time evolutions of the concentrations are calculated, and the plots are given in the figure. At the first glance, it looks like a first-order reaction. However, we can check the half-life of this reaction. The half-life of a second-order reaction depends on the initial concentration. For example, the decomposition of nitrosyl bromide is a second-order reaction. The plot of the logarithm of concentration versus time is not linear. But the plot of the reciprocal of concentration versus time is linear. The other type of second-order reaction is first-order with respect to two reactants respectively. The rate of the reaction is proportional to the product of their concentrations. The time evolutions of the concentrations of the reactants and product are shown in the equation and figure. A second-order elementary reaction is called a bimolecular reaction, in which two molecular entities collide to react. One example of bimolecular reaction is the decomposition of hydrogen iodide, in which two hydrogen iodide molecules collide to react. Another example is the alkaline hydrolysis of ethyl acetate, in which an ethyl acetate molecule collides with a hydroxide ion to react. A stepwise reaction is the combination of a few elementary reactions. The simplest mechanism of a stepwise reaction is shown below. The reactant reacts to form the intermediate, then the intermediate reacts to form the product. Both steps are unimolecular, and their rate constants are K1 and K2 respectively. For simplicity, suppose the initial concentrations of the intermediate and the product are both zero. The derivation of the time evolutions of the concentrations is complicated. Let's have a look at the result directly. The concentrations as functions of time when K1 and K2 are close to each other are shown here. The concentration of the reactant undergoes an exponential decay like a simple first-order reaction. At the beginning, the increase of the concentration of the intermediate is fast, because the fast production from the reactant. Then, it slows down because of the decrease in the concentration of the reactant. Meanwhile, the conversion of the intermediate to the product accelerated, leading to a decrease in the concentration of the intermediate at a later stage. At the beginning, the rate of the increase of the concentration of the product is slow, because of the lack of the intermediate. Then, it speeds up due to the increase of the concentration of the intermediate, then slows down again due to the decrease in the concentration of the intermediate. At the end, the concentration of both the reactant and the intermediate decreases to zero, while the concentration of the product reaches a maximum. When the first step is much slower than the second step, the concentration of the reactant decays exponentially like a simple first-order reaction. The concentration of the intermediate is always low, because the consumption of it in the second step is very fast. The concentration of the product evolves like a simple first-order reaction with rate constant K1. On the other hand, when the second step is much slower than the first step, the concentration of the reactant decays exponentially like a simple first-order reaction as well. But the concentration of the intermediate boosts to a high level, because the consumption of it in the second step is very slow. The concentration of the product evolves like a simple first-order reaction with rate constant K2. From the previous discussion, we can find that, in a stepwise reaction, if one step is significantly slower than all the other steps, it determines the overall rate of the reaction. Such step is called the rate-determining step. A rate-determining step is like a bottleneck, which limits the overall flow. For example, the oxidation of carbon monoxide by nitrogen dioxide has two steps. The first step is the reaction of two nitrogen dioxide molecules to form one nitrogen monoxide molecule and one nitrogen trioxide molecule. Here, nitrogen trioxide is the intermediate. The second step is the oxidation of carbon monoxide by nitrogen trioxide. The rate-determining step is the first step. Thus, the overall reaction is a second-order reaction with respect to nitrogen dioxide.